All right, I wanted to talk to you a little bit about the agent-based model assignment that we have this week. And you'll see that it's very, very vague. Create a new or existing, especially explicit agent-based model, or extend an existing, agent-based model that simulates something interesting. It can be NetLogo, R, can be Python, can be pretty much whatever method you want. The reason it's this vague is, again, I've never found a really good agent-based modeling package that works for a week or two inside of a class. NetLogo, if you don't know any, I would definitely go with that route. And up on the web during the learning module for this week, you'll see that I have a pointer to NetLogo Web, where you can actually go up and you can create models and modify them to some extent on the web. There's good documentation tutorials both for NetLogo, the web version, which is what you see here, and there's also a version you can download to your computer. That would be a one way to go. Then I also have some information on agent-based models in R, and a code sample on doing that. Another one in Python. This is a whole page when I taught this one semester, but the folks didn't know Python were disadvantaged, so I didn't feel I could do that. And this is a lab that I developed for NetLogo. So you're welcome to use any of these approaches. Unless you know Hexim or really want to spend time with it, I wouldn't go down the Hexim route because it's fairly challenging to learn. It might be part of your project if you want to do that. But there are a number of options. Again, NetLogo would be the one if you're not a programmer that I would go with for at least for this assignment where we have a short period of time. I also wanted to show you there's some fun things here. This is one of the reasons I like agent-based models is you can do things like simulate a mosh pit. Why? I don't know, but this is kind of a very typical agent-based model sort of design where you have people moving around. This case is a mosh pit. You have a flock strength, which is how close people bunch together. Do they bunch together a lot, or do they spread out throughout the environment? And then you have a series of other ones. So this isn't really one you can build, it's one you can change parameters for. Similarly, given the situation that we're currently in, I went ahead and created one myself in JavaScript. And here you can see that I have a series of agents. Oh, it doesn't quite fit on the Camtasia screen. That's too bad. You can see I've got a series of agents. Oh wait, actually what I can do, I'll change the height a little bit and restart it, and I can make it a little bit wider to make it more interesting. Now you can see the chart down at the bottom. So this is pretty typical where you've got agents. These little circles represent my agents. In this case there are people because I'm doing simulation of a disease or a spatial epidemiology model. So over here you have the cell size in pixels. I'd leave that at 10. As you saw, I can change the width and the height of the spatial area. It's done as a grid, so they're moving around in a little grid. And then you can change the number of agents. I can crank it up to 1,000, restart it. That's a lot. 100 is a good number. Kind of low for that screen size. Let's do it at 300 and see what happens. Then there's some other parameters I'll talk about a little bit, but now we can go ahead and infect one person, and we see the disease spread very quickly throughout pretty much the entire group. A couple of them over here, a little bit isolated. Oh, and they managed to not be infected. The curve that you see is actually going to have the number of uninfected individuals in green, the red that are infected, and then there's a black line to show those that died, and a green line would then be those that were no longer infected or recovered from it. Now the reason for that is the death rate is set to 0.5. If we restart with a lower death rate and we infect, we're going to see that the same number of people become infected. Pretty much everybody. Oh, got everybody this time. But then the death rate is only going to be a proportion of the population. And of course these numbers are higher than just about anything that's ever occurred in the human population. The plague, bubonic plague, was 30% death rate, I believe. It was one of the highest we've ever seen. AIDS initially was 100%, so that was kind of a scary one. Okay, so there's other things we can do. So you can change the amount that people are moving. Of course, the more they move, the faster it's going to transmit the spread. just as we're now under quarantine, if we let them move by, let's do it at 2, they're not moving as fast. Now when we infect someone, it's going to move slower. Okay. We can also change the attraction. So in other words, if we go to a negative, negative attraction in this case, which I think I have that backwards actually, you can see people are grouping. Now when they get infected, you're going to infect your group if you're the infected person, and maybe some people close to you. But that's it. It's not going to travel around. It's only going to take care of those folks. Similarly, if we go in the opposite direction, where things are spatially dispersed, not uniform, not random, but spatially dispersed from each other. I'm actually going to restart it. We can watch that happen again. This is done with a fairly simple algorithm where I pick a random place for each agent to move to, and then if it's closer to someone, and we want to move closer to someone, I take the move. If it's further, I want to move further, I take it. Otherwise, I reject the move. Now we reject someone. Oh, and look at it go. Interesting. So that must be because our infection distance, our transmission distance, was high enough that it made it even through here. So let's restart it. Same attraction level, let them get dispersed. Now I'm going to reduce my transmission level. And now when I infect, you can see it doesn't actually infect anybody. If we move up our transmission distance, suddenly it does infect a large number of people. So transmissions distance and the spatial distribution of people is important. Death rate played with maximum infection level. This is simply how high your infection level can go before you die. So if we restart it and we infect it with a lower time, it's just going to move it more quickly through the process. People are going to either recover or die off more quickly. So very simple agent-based model. You can take a look at the source code. This is written entirely in JavaScript in this one file. You can see how much code it takes to do this kind of simple agent-based model. It's about 500, 600 lines of JavaScript code, so not too bad, but it does take some code. All right, so have fun with agent-based models.